Thank you very much. Hello, everyone. Today, I will present my paper about adopted keystroke rhythm for password hardening. As many of us believe that textual hard passwords are highly unlikely to disappear in the near future. So I try to propose some mechanism that can add a layer of security to the textual passwords. And I will explain that in a moment. So this is the outline. First of all, I will introduce the topic, then I will say the contribution, then explain the mechanism, then I will show the experimental methodology, then I will show the results, and then I'll conclude the paper and present the future work. Okay, now adopted keystroke rhythm versus honeywords. Actually, this idea came across when I was reading the paper titled Honeywords, Making Password Cracking Detectable. I don't know if you have read this paper, but to summarize this paper, tries to disguise real passwords by adding honeywords to the real password in the password file. So the password file structure consists of the username and password. This is the normal one. But in their work, they propose to add more honeywords that resembles the real password. Sorry, they propose to add passwords that resemble the real password, but it's difficult to guess which one is the real password. And their work, they propose to add about 20 honeywords in addition to the real password. And they propose some mechanism to create passwords that are similar to the real password. So when I was reading this paper, I said, why can't we use only one password and save the headache of trying to create 20 different real honey passwords by adding, collecting the rhythm or the way users type their password characters. So in this work, then the next, it's like some people think that this is a keystroke dynamics. Actually, it's not a keystroke dynamics because in this approach, I ask people to key their password in a certain rhythm. And that rhythm has to be memorized by them when they want to access the system again. So as a user, you need to type in your password, and you need to create some rhythm. Like, for example, if your password is city of Bochum, you need to say CI. This is the first part of it. Then probably you pause for a few seconds or milliseconds. Then you continue TY. You type TY normally. Then probably you pause a little bit. Then you say of. So you type the O and F normally, then probably you pause. Then you say P, O, or PO. Then you pause probably, then you type the rest. And this is, so you create like a rhythm, and you need to memorize that rhythm. So what we do, actually, we collect the latency times between the keystrokes, and we classify the latency times into discrete symbols, fast and slow, according to some technique. So basically, this is the main idea. So it's different than keystroke dynamics. So in keystroke dynamics, actually, we try to understand the behavior. We collect behavior biometrics about users, so we understand how they type their characters, and we have to collect a lot of data. Then we need to analyze their way of typing. Then we can use that to either harden passwords or authenticate users later. So as I said, so password hardening mechanism that relies on an adopted keying rhythm of a user. This is the difference. So you need to adopt a rhythm, then we can collect that rhythm and we can use it later. So the user is aware that he needs to type a password and set a rhythm that needs to be repeated for proper authentication. So that this is the contribution about this work is we proposed a novel password hardening mechanism that is based on chosen password typing style. So you need to choose your typing style in advance. And we proposed empirical approach for selecting global threshold value because when we classify latency times into discrete symbols like for fast, F from fast and S from slow, we need to like find a threshold so we can judge whether this latency time is going to be classified as F or S. And then we also proposed a local threshold. So we have like, we used global threshold and local threshold to classify latency times. So now the mechanism, first we have like two phases. The first phase when the user sign up. So a user is asked to key a password with a certain rhythm 2 times. So we actually compare the 2 times. If the 2 times of keying the password have similar rhythm, we say that this is a successful sign up. If the user was unable to repeat the rhythm, he has to key the password again. And once the user was able to create 2 similar rhythms, so we sign up the user for the system. So of course we record both the password and rhythm. Now in the sign-in phase, the user enters the password with the rhythm. The system verifies both passwords and the rhythm. If both are, there's match, so the user is in. Otherwise, the user he can't access the system. So as I said, the rhythm is recorded as discrete symbols, F and S. F is fast and S from slow. So we record actually the latency time, as I said, and we created a threshold called global threshold, so in which we decide which discrete symbol we have to record for this latency time. So as I said, the global, we had a group of users, so we were searching for a global threshold for the whole users. So in which we classify the latency time for every user. While this is the global threshold method, actually the set of threshold values we used is, of course, what we did first, we conducted the experiments. Then we had classified set we decided that the set is going to be started from 100 milliseconds up to 4,900 milliseconds, which covers or spans the whole latency times of all users. So the minimum probably latency time was 100 something, and the maximum latency time for a given student was less than 4,900. So that's why we chose this set to cover the whole things. As I said, the range is chosen to cover the entire span of the recorded latency times. Then the minimum, since the minimum recorded latency time by a legitimate user was 90, and the maximum was 4,820. Now, this was the global threshold mechanism, and now the local threshold method. Actually, we collect the latency time for each user, then we calculate the average latency time, and we say if the latency time is greater than the average, this is slow. If it's slower than the average, this is fast. So depending on this method, we classified the latency times into F and S. So let's talk a little bit about the experimental methodology. Actually, there are 60 students or participants participated in this experiments. Half of them were considered genuine users. The other half were considered the imposter users. This is the prototype we created to collect data. So this shows that there are 2 phases the users can, 2 phases of the experiments, the sign-up phase and the sign-in phase. So the user, during the sign-up, were designed for genuine users. So when they sign up, they need to select a username and a password, and they need to retype the password again. So we match the rhythm of the first type password with the rhythm of the second type password. If there is a match, that is considered successful sign up. And then the user, the genuine user, goes into the sign-in phase, and he tried to sign 3 times using a username and password. While the imposter users go, well, I will talk about that later, but this is the simple prototype we used. And this is the demographic data. So we had like 28 males and 32 females. The age from 18 to 22, 29 students, and 21 from 23 to 30. And we had like 10 students more than 30. Okay, this is the first global threshold results. So before that, as I said, each imposter user were given the real username and the real password, and were asked to try to access the system. And each imposter user is asked to type in the password 3 times. So we had like 30 students times 3. That means we collected 90 pieces of data. And the same thing, we collected 90 pieces of data from genuine users. So we collected 90 from genuine users and 90 from imposters users. And this table shows the sign-in data, okay, under different thresholds. On the left side, we have H0, H1, H2, etc. to H7. This is the Hamming distances between the 2 passwords. So when we say H0, that means there is a complete match between the rhythms of the real password and the password, the entered password. So when H1 means we have one difference in the discrete values. At the end, we show a number of true positive and the number of false negative. We noticed that when the threshold was between 700 milliseconds to 1,100, we got good results in terms of true positive and false negative. So, but still, we have to look at the data from the imposter users to actually decide which global threshold should be considered. This is the sign-in data under different threshold values for imposter users. And also we notice that in the same threshold interval, from 700 to 1,100, we had good results. Like since the false positive was like 422 and true negative was 86, 88, 88. This is out of 90. So as I said, because we collected 90 pieces of data for each. So when you say 88, that means true and negative were 88 out of 90, which is considered, I think, is a good result. So now this table shows the precision, FAR and FRR under different threshold values. And we can also notice here in the interval from 700 to 1,100, the data shows good results in terms of precision, okay, in terms of FAR and in terms of FRR. So from the results, we can judge that the best global threshold value should be selected from the intervals of 700 to 1,100. Now we come to local threshold values results. As I said, for each user, we calculated the average of the latency times, and we classified accordingly. And this table shows the local threshold values for like 30 students. And this local threshold values experiment results. So we have the legitimate users and we have the imposters users. And at the end, we can see that for legitimate users, we have like 87 true positives and 3 false negative. So it's 87 out of 90. Well, like we're true positive, admitted truly to the system. In terms of imposter users, we have false positive 3 and true negative 87. And I mean, these numbers actually came by accident like this. I don't know. So I come to the conclusion. From the empirical experiments, I can say that this hardening method can be effective or is effective for protecting passwords. And also both global and local threshold values approaches produce similar results, actually. However, the local threshold, we recommended to use local threshold values because it's easier to calculate, because in terms of global, what we have done is after we collected the data, we did simulations to find actually what is the best values, well, what is the best threshold that produces the best values. So in terms of local, we don't have to do any simulation. We just, use the average, and that can be varied from one person to another. Probably if we do the experiment on a larger scale, that will be probably more clear. In terms of future work, we are planning to conduct this experiment on large scale, like hundreds of users or maybe 1,000. Probably that will judge the method in a better way. And also we think about testing this method against shoulder surfing. If somebody is watching you typing your password, whether that mechanism will be effective against this kind of attack. Also, in our experiments, we use only these two discrete symbols, fast and slow. Probably if we use more than 3 discrete, like fast, medium, and slow, that probably would add even probably better protection for the password. Also, we need to think about new methods of discretization of the latency times now, because in this work we used only the threshold value. Probably we can think about like using the average or median or some other statistical method that can help us in producing a better classification of the entire latency times. And this is about it. And thank you very much for listening. And questions, please. Yes.